the group's name is CBRE, and presently I am at Bhubaneswar, heading the business at Orissa. So this is what is my background. Coming to this carbon capture in built environment, this has some references with the military technology, and there are some patents also involved. So I will not be going into the deep into the design part and all that part. So however, I'll be covering what is the requirement of this, why it is required now, and what are the advantages of having this, and how it works. So, I will take my apologies for not sharing the design and that part, because there are some restrictions. So you can understand the military technology and all these things. So to start with, I'll start with one story, or you can say one small story of Navy. Just imagine you are at 300 meters underwater. I'm talking about submarine. So there's no window, there's no fresh air, just a sealed metal tube in which you people are there. Just imagine that. There may be 100 people, there may be 50, 60 people, and they all were breathing inside the tube. Now think carefully. Every breath releases CO2, and it releases more than 100, 125 times we inhale oxygen, or we inhale CO2. If that CO2 is not removed within hours, the people will feel dull, the decision making will slow, eventually the loss of the consciousness also. And there may be some fatalities also if it is built up more. So what do they do? What is the solution there? They don't ventilate. In our offices, in our buildings, what we say? We take fresh air and we dilute that CO2, and we carry on with we call ACH, air change per hour. But that facility is not there. So what do they do? They use amine-based systems, that is chemically bind CO2. Amine is basically an organic derivative of ammonia. That solution binds, captures, or you can say absorbs the CO2. And for oxygen, what they do, they split the water through the electrolysis. So this is the system in submarines. There is no dilution here of CO2, only removal. And just keep this in mind, because this will be requiring, you will be actually requiring to connect this or relate this with today's topic. Take another example. अभी 2 दिन से कल से, if you see, there's a war going on between Israel, Israel, America, and Iran. And Iran is a nuclear country. So are these countries. So just think how these people, if there is a nuclear attack, how the people will survive, how the military leadership will survive. Now take an example of a bunker, a 50 feet underground, say suppose in Rajasthan. The officers will be sealed inside during this in emergency if there is any contaminated air outside. So where is the solution? They cannot open it up. So there again, they capture this CO2, they absorb this CO2, but here in place of electrolysis, what they do for oxygen, they use oxygen candle. Dear friends, this oxygen candle is not a wax candle. This is a metal filled with a chemical mix called sodium chlorate. When an officer pulls a pin, a chemical reaction starts. It does not explode. It just gets very hot and glues. releasing enough pure oxygen to keep a room full of people alive there for several hours. And at the same time, they keep this as at the positive pressure also, so that the contaminated air from the outside is not entering into that bunker. So again, they don't depend on outside air, rather than they manage air internally. This is what is a technology on which I am going to discuss with you. So why it is required? Why I am talking about this military technologies in civil? Why this matters? If you see today, particularly you people, some of you might be sitting in Delhi. Our modern cities are becoming like these bunkers now. With high pollution in cities like Delhi or Mumbai, we often keep our windows shut and our ACs on. And the problem, we are hot boxing ourselves with carbon dioxide, which makes us tired, which makes us lose focus at work. And the future of this built environment will be, and starting is already started, that the architects are now looking at these scrubbers to build office building that can eat CO2, that can capture CO2. So our indoor air is as fresh as mountain breeze. In a regular Indian offices, we often feel like 2:30 or 3 o'clock after lunch, where we feel that sleepy. We get a mild headache also. And people used to come out of the office, walk here and there. We lose focus if we are sitting into the office. We usually blame it for the lunch. But actually, it is the CO2 buildup because the windows are sealed to keep the AC cooling in. And in Delhi and Mumbai, this is more severe. So this is where actually I am coming. So gentlemen, this is all happening because of climate change. We all know about climate change. If you see my slide on the right hand side on the top, you find up to say 1950, 1960, there was no, it was a constant line. The CO2 level, the GHG level, emissions level were almost constant. And after that, after the industrialization, there is a sharp hike to the GHG emissions. And what we develop, that climate change is often presented as an environmental debate or a potential issue, or a political issue. People talk now. There was some this thing, dharna and everything was happening in Delhi. But at its core, it's neither a political debate or issue, not an environmental issue. It is a mass balance problem. When I say mass balance problem, it means as engineers, we understand the input, output, and accumulation or flow, whatever you call. So every year, the humanity emits, or the human actions emits around 40 gigatons of CO2 every year. You can understand the volumes, that's 40 gigatons into the atmosphere. This is an annual inflow. And we we often heard that there is a temperature rise and all this. But this temperature does not respond to this annual emissions alone. It is not responding to this 40 gigatons. It responds to the total accumulation, stock of the greenhouse gases in the atmosphere. Think of it like a tank. There is in a tank, there is a tap. If you can relate this tap with the emissions. There is a drain. Drain is like a natural sinks. The oceans, forest, then the trees, even some agricultural activities. All these are the sinks. and the tank is the atmosphere. The water level is a global temperature. But here what you find, that if the inflow exceeds outflow, whatever we are sinking, if we are generating more greenhouse gas emissions we are releasing into the air, the level will definitely rise. The natural sinks absorb roughly half of the emissions which actually we are doing. The rest accumulates into the atmosphere. This accumulation actually is a balance problem, which I was talking about, and that drives the warming. So, according to the IPCC, if you say IPCC is the Intergovernmental Panel on Climate Change, the remaining carbon budget to limit warming to 1.5 degree is about 300 gigatons of CO2. From where this 1.5 degree comes, it comes from the Paris Agreement. We all agreed that we are going to limit our temperature to 1.5 degree above the industrial era. So now the only 300 gigatons of CO2 budget we have, and we are emitting at the rate of 40 gigatons per year. So now you can decide, this is just a mathematics. If you divide these 300 with a 40, it equals to the 7.5 years. So assuming emissions do not increase, if we say it is not increasing, then also there is accumulation. This is a hard system constraint now, as of now. As engineers, we understand the constraints. You cannot negotiate or you cannot argue with conservation of mass, and you cannot even negotiate with the carbon budget. It is fixed. So you cannot do anything there. So many discussions focus on percentage reductions. Like in all of the companies now talking about sustainability, ESG and all that. They say we set a target of reducing 5%, 10% or 20%. But the temperature rise does not respond to these percentages. It responds to the cumulative emission, not the yearly percentage. It responds to the area under this curve, which we are talking about. So if we delay action for, say, suppose for 5 years, and at the current rate of emission, we will consume 2/3 of the remaining budget within 5 years, and the safety margin collapses. So another critical issue is irreversibility. CO2 stays in atmosphere for centuries. Today's emission commit future generation to a long-term warming. The complete the climate will be warmed for the future generations. So to stabilize temperature, the net emissions must reach to zero. What do we call net zero? Not slower growth, not reduced growth. It exactly the net zero. Only when flow equals to outflow does the temperature stop increasing. But it will be only stop increasing. It is not going to reduce here. For reducing, we have to go to the negative also. So if we overshoot, we rely on carbon removal technologies. There comes the real solution, and that solution is if we remove this accumulation from the atmosphere. And one of them, the method available is a direct air capture. Another is, which is now coming up into the industry, is a biochar, which is basically from the agriculture side. So, but today removal operates at millions of tons of per year. As of now, if you say globally, it's only millions of tons which are being removed, and the emissions are tens of billions. So this is how the scale is now at present exist. This scale gap is enormous. So what we have to do, this is not a this is not an adjustment problem. It is system transformation challenge now. As accumulation increases, so does the risk of tipping point. Tipping point is where the ice is sheets or the ocean circulations, and you cannot, or any engineer cannot ignore low probability, high impact risk. This is a risk of low probability with high impact, and I will say very high impact risk when consequences are catastrophic if this happens. For those in the built environment like me, every project contributes. Through So every project contributes by the embodied carbon, by the operational energy, by the material choices, what we do to that 40 gigaton annual flow, which I was talking about. So if climate change is seen as environmental, it becomes someone else's responsibility. That's what I was talking about. If it is understood as a physics constrained mass balance equation, that becomes an engineering problem. So to make it someone else's problem, we are going to do or going to make it an engineer's problem or engineering problem, subject to design, optimization, and scaling. So if we say the carbon budget is a hard boundary condition, it cannot be expanded. It cannot be deferred also. Only real question is, how does this decision change the accumulation emissions trajectory? Because temperature is governed by accumulation. The integral of your decisions over time. That accumulation is what? It is the outcome of your decisions over time, which previous generation has taken. So climate change is not an abstract debate. It's a mass balance problem, and we running out of the storage capacity now. Going forward, when we talk about climate action, most discussion focus, and you might have heard about in your boardrooms, in your companies, the majority of the people talk about mitigation, clean electricity, electric vehicles, heat pumps, energy efficient buildings. We take green certifications. This sector, built our environment, which I'm talking about, account to over 70% of the global emission. These all sectors, if you combine together, like your energy side, your vehicle side, your heat pump, your building side. But mitigation has limits. Not all emissions from the burning fuel can be mitigated. Now we take an example of cement. There may be somebody in the audience who is from the cement industry. See, in cement production itself releases CO2, not only from kiln fuel, but from calcination itself. When limestone is heated, it chemically breaks down into the calcium oxide and CO2. So it is not a problem of energy. It's not a problem of secondary emission. It is a process itself which is generating CO2. Even if the kiln runs on renewable energy, renewable power also, though it is very difficult, then also the processing emission will remain. So the cement alone contributes, if you take cement, it alone contributing around 7 to 8% of the global CO2 emission. And in India, if you see, it is increasing by 88% from 2021 to 2030. If you take the 10 years period, it has to grow by 88%. If 88% means this emission, which is a process emission, will also be increasing by 88%. So inflow is much more. Take an example of steel. The traditional steel making uses carbon to remove oxygen from the iron ore. The carbon binds with the oxygen and forms CO2. This is fundamental reduction chemistry, not just fuel consumption. Now we are talking about green steel and green hydrogen and all this part. So these pathway are still in a, you can say, particularly in India, in a pilot phase. A very few green hydrogen, this thing, plants are operational now. And it requires massive renewable energy, massive hydrogen infrastructure, and the capital required will be huge. Then the water for electrolysis. In place of this should not happen that in place of CO2, we consume complete water itself. Take the case of aviation also. So these sectors are sectors which are hard to abate because the electrification alone cannot eliminate these emissions. When we examine the credible 1.5-degree pathway assessed by the IPCC on the climate change, the International Energy Agency also concluded that it's a constraint. So the mitigation alone is not enough. If you take all realistic net zero pathway require carbon dioxide removal of 5 to 10 gigatons per year by mid-century. So if we have to have this net zero coming up, then we have to capture this carbon, remove this carbon from the atmosphere. And today the engineered carbon removal operates at only millions, which I was talking about earlier also. But why this removal is necessary? Because even with aggressive decarbonization also, if you do, the residual emissions will remain. The cement, steel, aviation, agriculture, these sectors will remain. The strategy therefore has two parts. First part is reduce emissions as far as technically and economically possible. That reduction is through mitigation. Remove what cannot be eliminated. At two fronts we have to work upon. But again, the removal has its own limits also. If I'm talking, if I go out of the built environment side, then this removal will lead lot of land. There will be land competition, land requirement. There will be bioenergy. There will be the carbon for the carbon capture. High energy requirement will be there. Then again, if it is coming from fossil fuel, there is no use of capturing carbon because removing carbon, you are increasing carbon. And the capital requirements also will be very high. The storage, permanence, and the monitoring challenges will be there. There will be social and regulatory constraint also. So it's very difficult, rather, you can say. This means we are not solving one problem, we are adding new global industry now. The mindset which was there earlier, now it has to change completely to develop this into a new industry which is through the carbon management and at the scale of gigatons scale. The real challenge in the industrial transformation, if I was talking about, which is out of the built environment, the cement must evolve through clinker substitution. Can you substitute a clinker or carbon capture or alternative binders? Steel must transition towards hydrogen reduction and greater scrap recycle. Same way, the aviation must advance sustainability fuels, so sustainable fuels and new propulsion systems. At the same time, carbon removal must take a dramatical scale. So in all these scenarios, if you consider, the carbon capture is one factor which is going to be there. This is not incremental improvement. It's system redesign rather under the chemical, thermodynamics, and material constraints. So the logic straightforward is mitigation reduces emission, hard-on abate sector create residual emissions, and carbon removal neutralizes that residual emission which hard to abate can do. So without removal, net zero is mathematically not possible. The issue is not whether we need mitigation and removal, we clearly need both. Now coming back to the built environment side, we spend around, you can say 80 to 90% of our lives indoor, whether it is a home or it is an office or a school or hospital. Yet most air quality discussions focus on outdoor pollutions only. Outdoor CO2 levels are about 450 ppm now. And the indoor CO2 commonly rises to 1,000, even up to 3,000 also. You might have seen in your offices if you are monitoring that. And majority of the offices are even not monitoring that. So in engineering practice, CO2 is used as an indicator of ventilation adequacy. When level rise, we increase fresh air supply. The air from the atmosphere is taken in and we dilute that. That works if the outdoor air is clean. In case of Delhi, can you afford to have in the month of, say, suppose October, from October to February, can you take that air in to dilute the CO2? But if you see, the indoor air quality is not a single variable problem. It is a multi-parameter system. You will have CO2 from the occupants. You have particulate matters that is particularly PM 2.5, PM 10. You have VOCs. You have nitrogen oxides and ozones. You have biological contaminants also. So building is a control volume. The pollutants are generated indoor, or it can infiltrate from outside also. So the concentration of these contaminants will depend upon 3-4 factors. One is generation rate, with which rate it is being generated. Another is ventilation rate, how we means the air change per hour, which we in office is called. Filtration efficiency and outdoor pollutants level, because the air which is coming from outside will have the pollutants. So it depends upon all these. So indoor, say suppose PM 2.5 in urban India often ranges between 50 to 250. Now I'm sitting in Bhubaneswar, it is in between 50 and 100. Far above the World Health Organization, though the Bhubaneswar is considered as one of the cleanest city. And the World Health Organization recommends only 15. That is annual average. In Delhi especially, from November to February or October to February, the severe smoke episodes occur due to the crop burning, traffic, industry, construction, whatever you take. The AQI exceeds 400. PM 2.5 can rise up to 300, 500. So here lies the ventilation dilemma. Now, this ventilation I was talking about, diluting the CO2 level, diluting the pollutants. If indoor CO2 exceeds 1000 ppm, the standard approach is to increase outdoor air intake. But when outdoor air itself contains extreme particulate pollution, bringing in this air inside without high efficiency filtration Simply it is the transferring of toxic particles inside. So if we reduce, these pollutants have very different risk profiles. The 3-4 pollutants which I was talking about. If you take CO2, CO2 at 1500 ppm may impair the cognition and cause discomfort. PM 2.5 penetrates deep into the lungs, enters the bloodstream, and contribute to even heart disease also, stroke and premature mortality. This is what is its severity. So during severe smoke, the fresh air becomes a pollutant source. From a mass balance perspective, if you say for CO2 accumulation, the indoor generation minus ventilation. That's what is a formula for CO2. But for PM 2.5, this accumulation inside your office or inside any this thing built environment, the outdoor filtration plus indoor sources minus the filtration or the disposition if it is possible, it depends upon that. So if outdoor PM 2.5 is very high, increasing ventilation, increasing particulate inflow, even if it lowers the CO2. When you take inside air, the CO2 level will go down, but at the same time, you are increasing the particulate matters, which are more dangerous than even CO2. This is a coupled system. One variable cannot be optimized in isolation. So where is the solution? Solution is not simple more ventilation, but it requires demand control ventilation. It demands high efficiency filters. That's HEPA or equivalent. It requires air purification systems. It requires energy recovery ventilators with the filters. So multi-parameters indoor air monitoring is required. In polluted cities, building must shift from this dilution-based design to filtration-based design. Here comes the role of capture. Many ventilation standards we developed in regions with relatively clean outdoor air. Where the outdoor air was clean, this ventilation system, this dilution-based design were okay. Applying them without adaptation in the high pollution environment increases unintended health risk. And this is a public health issue. During winter smog in Delhi, if you see the schools closed, the people are advised to stay indoors. And surprisingly, indoor environment is more polluted. Because of CO2, because of PM 2.5, we are boxing our houses, closing our ventilation part. Even if we do not close, then also we are taking more particulate matter inside. Only the indoor is only safer if the air is engineered properly. And there is also an energy link. Higher filtration increases. If you increase filtration, the fan power will increase. The consumption from electricity will increase. High fan power will increase the energy use. If then energy comes from fossil fuel, against the emission increases. So if in place of removing CO2, in place of capturing CO2 or replacing CO2 with a fresh air, what you are doing, you are emitting more CO2 into the air. So indoor air quality is not just a building service concern. It's an engineering optimization problem across health, energy, and climate performance. So the ventilation is not automatically beneficial. In polluted environments, uncontrolled ventilation transfers contamination. The goal is not more, but fresh air. and it is fresh and clean air. And city like Delhi during winter, that dilution is really, really critical. The air changes per hour is, we just consider this as a regulatory value कि वो एक मेरे को compliance पूरा करना है, but it represents how quickly the indoor air is replaced. In simple terms, how effectively the pollutants are diluted as of now, which we are doing now. In a steady state model where indoor CO2 concentration is inversely proportional to the ventilation rate, but if it is a ideal condition, steady state condition, if we treat a room as well mixed control volume, the steady state concentration is always equal to the generation rate divided by its ventilation rate and its volume. If you reduce ventilation, the CO2 will increase. If you increase ventilation, CO2 will fall. This principle underpins the global ventilation standard, which is there as of now. But this logic assumes outdoor air is clean. This is only applicable when your outdoor air is clean, which is not in Indian cities now. Now consider a Delhi winter smog episode. Outdoor AQI exceeds 400. PM 2.5 can range 300, 400. If we increase air change per hour under these conditions, we increase the inflow of polluted air. So what is the trade-off? Now the lower ACH, air change per hour, reduces outdoor particulate entry. The indoor CO2 accumulates, cognitive performance declines, your occupant comfort suffers. If you increases the air change per hour, the CO2 will increase. Then the high PM 2.5 enters. Filter will be clogged quickly, and the pressure drop rises. Fan energy will increase. The filtration is really weak because it's already clogged. So we are forced to inhale hazardous particles. This is not a simple problem of environment. This is a safety and thermodynamics trade-off between two risks: performance degradation or elevated CO2. So long-term cardiovascular and respiratory damage from the particulate exposure will take place. And the filtration adds another layer. That means the extreme particulate loading, faster filter saturation, increased pressure drop, higher fan energy consumption, the operational cost and carbon impact will increase. And if the building is poorly maintained, the further reduce its effectiveness. So the solution comes only with the carbon removal or carbon capture. We normally do that. This is how is a effect of this CO2, how it basically affects the human when they are exposed to. The research shows the 1000 ppm CO2 is start affecting your cognitive decline actually begins. And the controlled study reports that reduced decision making quality, weaker strategic thinking, and slower crisis response as CO2 level rises. At 1500 ppm and above, impairment becomes clearer. Slower reaction time, reduced information processing, and loss of focus. And in high-stake environments where the control rooms, engineering plants, your financial operations, this is not a comfort zone. It is a performance issue when professional operating daily In elevated CO2 conditions, the mental sharpness declines. But CO2 is only part of the picture. In cities like Delhi, during winter, PM 2.5 levels often remains far above safe limits. The fine particles penetrate deep into the lungs and enters the bloodstream. This is documented impacts, and that includes increased cardiovascular stress and blood pressure, systematic inflammation, worsening the respiratory conditions, gradual reduction in lungs function. All these are the parts, or all these are the effects of it. If it is reaches 2500, there will be adverse health effects expected. At 500, if it reaches, it's really fatal to have exposure, and that can the man can collapse also. So that is what is the consequences of this. If we talk about HVAC now, that is basically an energy burden. The HVAC system typically account around 30 to 50% of a building's total energy use. In hot weather, the high occupancy commercial buildings in India, this can exceed up to 60% also. And that is already a major energy load. When indoor CO2 rises, the conventional response is to increase ventilation. So it increases the energy consumption also. The fan power rises, the cooling demand increases, and electricity consumption grows up. This creates a paradox here. We use carbon intensive energy to dilute carbon dioxide by taking more air in. Reducing indoor CO2 by ventilation can increase indirect CO2 emissions. So the ventilation carries a seasonal energy penalty to us, high cooling loads in summer and high heating loads in winter. With this comes the actual where how we can resolve these problems. And the introduction to the direct carbon capture is here. Direct carbon capture is usually discussed in planetary scale. At a bigger scale, at industry level. So large plants, the pulling CO2 from ambient air at 420 ppm. Now it is on average in the outdoor air is having 420 ppm, which is around, you can say, 0.04%. That concentration is extremely dilute. Roughly 1 CO2 molecule per 2500 air molecules. That much is a concentration here. So processing such vast air volumes make ambient direct air capture energy intensive. So there will be more energy required if we take the normal air which is there in an environment, if we start capturing CO2 from there. So by comparison, if you take a case of a coal plant, flue gases from the coal plant or a cement plant, it contains around 5 to 15% of CO2. And if you calculate that, it comes out to be around 50,000 to 1,50,000 ppm is the concentration of CO2 there. So this higher concentration means higher pressure and stronger thermodynamic driving force. So this makes the separation more efficient. From there, if we start capturing, it becomes efficient. The energy uses will not be that much. This is about the industrial and more CO2 concentration part. If you come into the in-built environment side, inside the building, the indoor air, it comes in the middle ground. It is not that the concentration is not that much as per the industry or cement plant or coal plant, or it is not also in the 420 range, which is outside. It is in between. So occupied building routinely operates around 800 to 3000 ppm CO2. The permissible limit is 1000, but it always crosses into the built environment. So the 2 to 7 times occupied building routinely operates at this level. That increases the concentration and that improves the separation efficiency and reduces energy per unit captured compared to the outdoor direct air capture. So this creates an engineering opportunity for us that selectively the indoor CO2 we can remove, integrate that into HVAC systems also. So instead of increasing ventilation to dilute CO2, which we were doing, which was more energy intensive, our approach should be that we remove the CO2 directly from the recirculated air using solid scrubbers, liquid absorption system or membranes, which I was talking about in the starting, was when I was giving example of submarines or bunkers. If we use the technology here, we can remove that CO2 directly, and not only CO2, it can capture PM 2.5 or all particulate matters, in even the biological pollutants also. So there comes the actual technology which can be used. How an active atmospheric building works, if you say in that situation. You imagine a technological park, say suppose in Bangalore or in Hyderabad, designed as carbon managed building. It operates in 4 coordinated stages. There are 4 different stages of this. First is high grade filtration. The outdoor air passes through CBRN grade filters or filtrations. CBRN grade is a terminology used extensively in military. CBRN means chemical, biological, radiological, and nuclear. All these filters capture these contaminants, similar to system used in military environment. What these filters do, these filters will capture PM 2.5, PM 10, black carbon, traffic related VOCs, volatile compounds. This prevents particulate heavy air coming, common during severe pollution episodes for example, in Delhi, from degrading indoor conditions. The second step is chemical CO2 scrubber. This filtered air, which is filtered through the CBRN grade filtration, moves through a scrubber module containing amine coated mass or structured packaging. This amines chemically captures or binds CO2 while its nitrogen or oxygen passes through. This chemistry is already used in submarines, which I was given from which I started, and it is used in INS Arihant to maintain a breathable air in the sealed environment. In the buildings, the objective shift from life support to performance optimization by the carbon management here. This captured CO2 is periodically released by heat or pressure pressure swing regeneration, and can be compressed for storage. So what we are going to do this with this CO2? This CO2, which is a, you can say, a hazard for us, is actually the feed for the plants or for the agriculture. So this can be used there. So we can decompress this for the storage and use it there. Use in some industrial applications also. And it can be fed into the biological system. So this is one. Another part is, the third stage is bio regenerative facade. This is, we already have one building in Bangalore which is using bio regenerative facade. This is an advanced design which integrate algae filtered facade panels. We call it bio curtains. The concentrated CO2 feeds these panels, where photosynthesis converts the CO2 into oxygen and increases the biological carbon uptake. So this there becomes the oxygen enrichment. Third, the last step is intelligent control system, that is IoT integration. A sensor network monitors CO2, PM2.5, humidity, temperature, and occupancy in real time. Instead of defaulting to higher ventilation, which we normally conventionally do when rooms fills up, the system increase this intensity of filtration, or scrubber intensity increased. Optimize the recirculation of the air. Adjust the regeneration cycle dynamically. The building becomes a controlled atmospheric system rather than a passive passive air exchanger. Why this matters? Why it is important? This approach delivers three different advantages. Cleaner indoor air without importing pollutants, because when we were taking air, or when we were opening our ventilations, the more imported air or that was polluted was coming in. It lower energy use by minimizing the excessive ventilation loads, so the energy will be saved. Distributed carbon management at the building scale. So these were the three advantages we'll do. The commercial complexes, campuses, airports, malls would function as decentralized carbon removal nodes. In place of emitting GHG, at built environment have around 40% contribution to the GHG, they will be removing the carbon. So that is a complete shift. The shift is fundamental. From the dilution to selective removal, from passive ventilation to active molecular energy engineering, from energy heavy conditioning to smart atmospheric control. So the direct air capture layers higher indoor CO2 concentrations to improve efficiency while protecting the occupants from the outdoor pollution cycles. In high density, high pollution cities like Delhi, the buildings can evolve from energy consumers into active environment regulators. Cleaning air with precision, managing carbon locally, and decoupling the indoor health from outdoor smoke. This is what is happening in Delhi. So this is what is the advantage of this. Now going forward, if you say, here, if you see earlier, what happens? There were, I'm talking about when we were in control. At that time, the trees, plants, all these were supplying oxygen because of their photosynthesis. Their oxygen were released into the atmosphere, and people or human being or animals used to take that oxygen, and then it goes into the food and chain. There is a closed cycle there. But what happens over time? Over time, this cycle was broken. So now with this direct air capture, we can reintegrate or we can redesign this cycle by adding this carbon capture into the system. How we can do that? Just give me a minute. How we can sorry, how we can do that? There is a these filters and these capture carbon capture devices in place of oh sorry in place of directly it is going to the tree and plants. Now we are passing it through these filters, or we call it bunkerment technology. From this bunkerment technology, it is going back to the organic manure. It is converted into the organic manure. The residue which is captured from these filters is actually converted into organic manure. It is going into the agriculture, into the plants and all that part. And then plants and this will further give us oxygen. So like this accumulation problem and this problem of CO2, which was actually accumulated much into the atmosphere, is removed, and at the same time the air is the CO2 is not rediverted or is not entering into the atmosphere again, but it is actually utilized into the your agricultural part and your even in the concrete also. And this system which I was talking about, there's one case study also which is there uh, in Guwahati. In Guwahati, sorry, there's some reason. This is a case here. This is one case study which is of oil refinery Guwahati. What you see here, there are two parts of it. One part is you see the different boxes. These are these capture devices, filtration devices, carbon capture devices. These are placed into a data centers of the oil refinery. Why in data center? Because in data center, this moisture, CO2, all this part is very important. At the same time, the ACH, air change per hour, consumes lot of energy. So by this, they have reduced this energy level to 30%. This is already proven there. And the bottom picture, if you see, this bottom picture is of their office. So they are using it as their office also. And this CO2 level actively now maintaining at 600 to 800 ppm, well within the optimum cognitive performance range. The fresh air exchange was drastically reduced from 0.66 air changes per hour to just one air change per hour now, which they were earlier doing 0.66 air changes per hour. Now they are in a 24 hours, there are only one air change is required. And that is a fundamental shift in the philosophy. Rather than continuously importing outdoor air for filtration, the system relies now on the controlled internal conditioning and pollutant management. What other benefits it has bring? Because the facility was no longer constantly cooling, now the dehumidification and filtering range large volumes of outdoor air, the cooling load dropped drastically. Instead of operating at the original design for two ATTR chillers, now the facility could function with only one ATTR chiller. So that chiller gap also is reduced, around 50% reduction. This company Bunkerman actually claims 50%, but oil refinery confirms that it is 30%. We have already measured. So this is how is the impact of this. There was actually a sequence problem. This slide was before, sorry, after that, but it has actually added in between. So let me cover that also. Now this carbon which are capturing, this can be added into the biochar. Biochar is a agricultural output now which captures, which stores carbon dioxide and used in the agriculture field or compost activation also. So a stable organic carbon is mixed there. Another use is that we can use this into uh, concrete, mix this into the concrete, which physically and chemically stabilizes this by adding this carbon into that. So with this, actually, I'm done with my today's session. This is a new technology which we are starting in the built environment. I am from the same field, from the built environment only. Though it is new, but yes, this is very effective and may form some. So may, in future you may see a lot of traction onto this. If you see the carbon market itself now, the carbon capture is already added into that. So you can even earn credits also if you are using this, because this will be this system will be completely giving you data, which data, how much carbon it has captured, how much this thing energy it has saved. All this data they will already be providing you. So the another added you can say revenue source can be a carbon credit also going forward. Any question, anything if you want to ask me, I'm open for that. Hello.
Hello. Good morning, sir. This was
Yeah,
nice
good morning.
presentation. Myself, Rahul. It was nice presentation done by you. I
Thank
just
you.
want to know where
Thank
we can get those filters and all the things, because this we heard the new systems for the green
you.
buildings and all things. So
Yes.
can you give some reference and all the things so that we can go for the for
Yes,
the
yes, yes, Rahul. I'll definitely give. I'll share my mobile number also here in the chat.
yes.
And from there you can take my number. I'll definitely align with that. And this is being used now in Gurgaon also with the DLF. It is again a pilot project, but there are some NDA clauses because of which I'm not able to give you the names of the buildings and all that. But yes, it is being used now. And IIT Ropar and IIT Madras is already working on this. So it is coming from that side also, and it is coming from the defense veterans also. So there is one organization which is called Bunkerman. Dr. Siripal, he is actually pioneer of this technology in India. He was a scientist in the nuclear this thing bunker development. So he actually brought in this. He has taken that permission after COVID because COVID actually opens a lot of door for using these technologies into the civil, because this
Yes.
gives another advantage of we call button up period. Button up period means the person is staying into a closed environment, isolated completely from the outside for a longer period. That is called button up. Now, if you see the war is happening in Iran, there definitely the military leadership, political leadership will go into the bunkers, and that bunkers will be isolated completely. So that will provide oxygen also there, that will provide CO2, everything there. No, sorry, CO2 will be removed, oxygen will be provided continuously to these bunkers. Yeah.
Okay.
Yeah. Thank you, Rahul. Any other? Any other question? No.
Hello, I am audible.
Yes, yes, you are audible.
On behalf of everyone here, I would like to extend our sincere thanks to our speaker for insightful and inspiring presentation, and to our
Thanks.
wonderful audience, thank you for your active participation and thoughtful engagement. Your presence made this event truly meaningful. Thank you, everyone. Thank you, sir, for a
Thank
wonderful.
you, thank you, thank you, Yogaraj. Yogaraj, I am sharing my mobile number, or you can share my mobile number. So anybody want any further information can reach out to me.
Sure, sir, sure.
Thank you, sir.
Thank you, boss.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you
sir.
very much.
Thank you very much, sir.
Oh, thank you, sir. Thank you.
Thank you so much.